In 1943, the US Ordnance Department contracted the University of Pennsylvania to develop an electronic computer to solve complex equations in the field of ballistics. That computer, completed in late 1945 and known as ENIAC, was arguably the first electronic computer. ENIAC filled an entire room and used vacuum tubes as its basic building blocks. This was fast compared to previous electromechanical devices, completing up to 5,000 operations per second. Its major drawback, though, was that it had hard-wired instructions set by dials, plugs and switches. In 1944, the mathematician John von Neumann became involved with the ENIAC team's discussion on a new improved machine called EDVAC. This machine was going to be capable of storing its programs internally in a memory system. This basic structure became known as the von Neumann architecture, and its concepts are those from which modern computers are built. With EDVAC, inputs were instructions coded onto, for example, punch cards and teletype tape. The output results were printed on a teletype printer, for example. Today's computers are a lot more powerful and smaller than the first ones. Here's a board from a modern computer, and here's the CPU and memory. Together, the logical parts of the CPU, memory, input and output make up the von Neumann architecture. Let's look at some of those parts in more detail. First, we need something which can carry out basic arithmetic instructions such as add, subtract, multiply and divide, and logical operations such as AND, OR and NOT. This is the Arithmetic and Logic Unit, or ALU. Whilst doing calculations, we need somewhere to put our temporary results, and this is what the temp area is. It contains blocks of fast memory called registers, and we'll see more of them later. Together, the Arithmetic Logic Unit and the registers form a processing unit. Next, we need a place to store the calculation instructions and its associated data. We call this place the main memory. Memory is just a sequence of storage locations inside of which is the binary data. Each memory location is accessed using its address, which is a number much the same way that a home has an address. Often addresses are shown in diagrams as hexadecimal or base 16 numbers, although of course from the computer's point of view it's a binary number. To access and move data into and out of the main memory, there are two special registers. The Memory Address Register, MAR, stores the address of the memory we're interested in, and the Memory Data Register, MDR, holds the data fetched from that address, or the data which is going to be stored at that address. These address and data registers are used only by the CPU and are not accessible to programmers. Finally, we need a way of controlling the sequence of all of these operations so that the fetching of instructions, the triggering of the calculation, and the storing of results is done in the right order. This is the job of the control unit, or CU. There's two parts to this: the program counter, PC, which holds the memory address of the next instruction, and the instruction register, IR, which is the actual instruction currently being executed. For each and every instruction, the CPU follows the same basic steps of fetch, decode, then execute. Fetch involves using the program counter to get the next instruction from memory and storing it in the instruction register. The instruction is then decoded and, depending on the instruction, more data may be fetched from memory and stored in the temporary registers. The instruction is then executed, for example adding two numbers together, and the results then stored. Let's see how all of this works by looking at a simple example in more detail. If I wanted to use a computer to add three numbers together, 2 plus 3 plus 5, what would be the steps? Since a computer works by executing instructions given to it in its own machine language, then ultimately we need to prepare those instructions in the form of a program. Fortunately, computer scientists in the past have invented higher level languages that humans can understand, and which are then converted into a language the machine can understand. Here's an example of a program written in C++, which will add the three numbers together. It could have been written in a much better way, but this is just for illustration. First, a variable called data is used to store the numbers we're going to add together in an array. Next, the result variable is initialized to 0. Finally, a loop is used to add the result to each number in the data array, so at the end of the loop, the variable result will contain the answer 10. C++ is an example of a high-level language in that its syntax isn't dependent on any particular type of CPU. Here's the same example but written in a low-level language called assembly language. This is a language much closer to the machine language that a computer uses and has a syntax which is specific to a particular type of CPU. So for example, you can see that it knows about how many registers the CPU has and what instructions it can carry out. Both high and low level languages need to be converted to machine code before the computer can run the program. High level languages are generally turned into binary machine code by a process known as compilation. Compilation is done by a compiler program that knows how to change, in this case C++ syntax, to the instruction set of the computer and hence to machine code. Low-level assembly language, on the other hand, is turned into machine code by a process known as assembly and is carried out by an assembler. Let's take a closer look at the conversion of one of the assembly language instructions, the load R1 data address. For this example CPU, the instruction means load register 1 R1 with the data that's held in memory address given by data address. All machine language instructions follow a particular syntax where the instruction operation is given first, then the data for that operation is given next. The instruction operation is called the opcode and the instruction data is called the operand. For this instruction, the opcode is LD for load and the operand is DR PC offset, which is the destination register and the memory offset to find the data. Remember that the computer only deals in binary form, so this actual instruction is turned into this binary instruction. Load is defined as the instruction number 2 or 10 in binary, whilst the destination register and address is encoded in the remainder of the binary information. For this example CPU, each instruction is encoded in 16 bits, whereas most modern CPUs use 64 bits. Now the details of these actual codes in binary forms are just examples, of course. The key point to remember is that the programming language needs to be turned into machine code and that the instructions are encoded in a specific and precise way. At the end of this process, we have the binary machine code, which can then be loaded into the computer's memory and executed. Here, each line of binary digits corresponds to either an individual instruction or a block of data. In fact, you can see that the last 4 lines are data rather than instructions, and have the numbers 2, 3, 5 and 0, which correspond to the 3 numbers we want to add together and a place to store the result. Once we have our program turned into machine code, it can be loaded into the computer's memory to be executed. Each memory location is accessed using its address, which I've shown here in hexadecimal notation for convenience. You can see that our program has been loaded at memory location hexadecimal 3000 and that the contents of this location is the binary form of the first instruction. Well, that's the program loaded into memory. Let's see the Fetch-Decode-Execute process for the first instruction, the load R1 with data address. First, the program counter is loaded with the address of the next instruction, which is our load instruction at address hexadecimal 3000. The computer's operating system will do this rather than our program. So the program counter is loaded with this binary word, which is the same as the hexadecimal one. Now the CPU starts the fetch step. The contents of the program counter are copied into the memory address register, and a read signal is sent to the memory, which results in the contents of that memory location being copied into the memory data register and then finally into the instruction register. So here, hex 3000 is copied into the address register, the memory location is read, and the contents of that is copied into the data register and then the instruction register. At the end of the fetch step, the program counter gets incremented by 1 so that it's ready for the next instruction. At this stage, the CPU has loaded the instruction but doesn't yet know what to do with it. This is the decode step. Since it knows the format of its instruction in terms of opcode and operand, and it can decode the instruction into a load R1 from an address. For this example, the address is given as an offset from the program counter's current value, which is address 11 steps, or binary 1011, which equates to address 300C. At the end of the decode step, the processor has all of the information it needs to be able to execute the instruction. The exact details of the execute step obviously depends on the instruction, since for example a load instruction is very different to an add instruction. In this example, the instruction to be executed is load from memory and place that in register 1. The CPU therefore sets the memory location 300C into the memory address register and issues a read to memory. The contents of memory address is then copied into the memory data register and then onward to its final destination, register 1. So register 1 now has the hex value 300D, which is of course the memory start address of where our three numbers 2, 3 and 5 are stored. That's the Fetch-Decode-Execute cycle for the first instruction of our program. The program counter is primed ready for the next instruction, and as you might expect, the processor repeats the whole cycle again for each and every instruction thereafter. Well, there we have it, an introduction to the von Neumann architecture, a model of computing that's still the dominant one in use today, storing both instructions and data in memory, having input and output devices, and a CPU which follows the Fetch-Decode-Execute is what defines this model. Now, there are many more details of how CPUs are designed and other new computer architectures which I hope to cover in later videos.